Okay, can you see the slides on the screen? All right, good. So let's move on with sputtering system. So last time we have discussed about the sputtering process briefly. So now let's get into details for sputtering. So to be able to run a sputtering process, you need a chamber. You need a chamber or space that that will host the sputtering process. Okay, so in this case, you can see this whole space. This whole space is a chamber. Okay, so that is a chamber. And then you need the gas in order to provide the ions. Vacuum. So typically we evacuate the chamber boleh dengar saya? Can you hear me and see me? I'm not sure if you can still hear me.
Doctor can hear you.
Okay. Oh, lagging, right? Tiba-tiba ada line internet ni. Saya pakai USM Secure juga sekarang. Sekat-sekat Alright. Hold on. Hold on ya. Yeah, line looks okay. Tapi tadi ada notification internet problem. Okay, let me just share again. Oh, ada problem, just type kat chat box so that I know what's going on. Nanti kan saya continue je tapi tak dengar pula. Okay. So base pressure 10 to the power minus 5. And when you have reached the base pressure, when you've reached the base pressure of 10 minus 5, then we inject the gas into the chamber. In this case, we use argon, and you create the plasma. Okay, so the moment you've got the plasma, we call that pressure as process pressure. Process pressure. So the first is base pressure, 10 minus 5. So the moment you've got a plasma, the process pressure is typically 10 minus 3. Because you've got your gas injected into the chamber already, and that will increase the pressure of the chamber to 10 to the power minus 3. Okay. Then power supply to create a large voltage drop between electrodes. Okay, large voltage drop between electrodes in order to initiate a plasma. Okay, if you fail to generate plasma, maknanya kalau you look through the glass window and then you don't see anything going on, tak ada color, tak nampak plasma, so there will not be any sputtering. So tak ada sputtering because there is no plasma to begin with, right? So you will be sputtering the target off. You'll be dislodging the atoms off the target when you have the plasma. Okay. So target in this case is the sputter target that you want to remove or you want to knock off for the deposition process. So it's sputter target. So that is the basis of a sputtering process. Okay. So for example, in this case, you use ITO, for example, ITO target, and then you have a huge wafer holder holding a couple of wafers, for example, and then this wafer holder or substrate holder is rotated, okay, in order to ensure uniform deposition, okay, uniform deposition. So in a sputtering system, you have plasma. So it's a mixture of neutron atoms, molecule, roughly equal number of positive ions and free electrons in a quasi-neutral state. Say argon gas is used as the sputtering gas because it is inert and it doesn't involve in the reaction during the sputtering. Okay, so this one is the very same thing like what we discussed on the previous page. You have gas cylinder, you have vacuum, you have grounding, you have the voltage to initiate the plasma formation, and then cathode and anode in order to create the plasma in between. And these are our electrodes. So that is your plasma. Argon plus in between electrode. So this is DC sputtering. Okay, DC powered. So direct current sputtering process. I have some problem on my screen. I'm not sure whether you can hear me. Not sure. Boleh dengar ke sekarang?
Boleh, doktor.
Okay. Do you see my full screen?
Yes, doctor.
Okay. Sebab saya tak boleh tengok plasma. Dia punya title kat atas tu saya tak nampak for some reason. And bila saya klik kat atas tu, it doesn't come down. Tak apalah, kalau boleh nampak, then it's alright. So these are the steps involved in order to create plasma in the chamber. So the first one, you need to supply the voltage between the electrodes. Now you can see you have anode and cathode, and then you have plasma in between. So you need to apply a voltage drop in between the electrodes in order to in order to convert your gas into ions, right? So that will strip your valence electrons off and create AR plus. So breakdown voltage, breakdown field of gas is exceeded. If your breakdown field of gas is exceeded, that will create a large number of ions and free electrons. Okay, so large number of ions and free electrons. So you started off with argon, and then you remove electron, then you're going to get AR plus. You're going to get AR plus. So this ion removal is done by the the voltage drop across the electrodes. Electrons are then accelerated towards the positively charged anode, and ions
Ish, nampaknya data hilang. Ifah jadi host.
Okey, boleh dengar ke? Nampak saya ke? Tiba perlu lock device ni. Right, thank you. Let me reshare. Share plasma formation. Okay. Okay, can you see the slide on the screen? Just to confirm. All right, thank you. Okay, plasma formation. Voltage is applied between the two electrodes. We saw that on the previous page, the positive and negative anode and cathode. Then at the moment you exceed the breakdown field of gas, and then we got to create ions and free electrons. So we use argon gas as our precursor gas for the plasma. So Ar minus electrons, and we're going to get Ar plus. So Ar plus will form the plasma in this case. And then during the acceleration to the opposite polarities, electrons will be scattered. Okay, electrons are accelerated much faster due to the small mass. Ions that strike the cathode generate secondary electrons, right? So you have your cathode on, and then the ion Ar plus. So upon collision with the cathode, say if you say that is a collision, then that will generate secondary electron. Okay, secondary electrons. Secondary electrons are attracted towards the anode if the field is high enough. Electrons require enough energy to ionize neutral atoms and molecules, therefore sustaining the plasma. Okay, so they can continuously generate Ar plus. It will collide, generate electrons, and then it'll be accelerated towards the anode. And then electron yang ada tu dia akan ionize neutral atoms and molecules in the atmosphere dalam chamber tu. So that will create the next ions and so on and so on. And that will sustain the plasma in the chamber. Okay, you can you can represent all the steps just now as this: dissociation and ionization, excitation. Okay, what gives, if I can ask you the question, what gives the plasma its respective color? Macam mana plasma tu dia ada cahaya? Kenapa dia ada color and cahaya? Anyone? How do you get the light during the plasma punya creation? Anyone knows? Siapa tahu tolong share dekat chat box. So during ionization, energy transferred is more than the ionization potential. For example, if you talk about argon gas, then you need to use energy of more than 15.7 electron volt for ionization process. Okay. So that will create secondary free electron and positive ions from the reaction, from the ionization process. Excitation. So upon excitation, that will take around 10 to the minus 8 seconds. So the returning to ground state, the excited particle will go down to the ground state. Dan apa jadi bila diturun ke ground state? When you have your excited particle go down to the ground state, what happens? What do you get? What do you call this process? Anyone? Proses ni kita bagi apa?
Recombination.
Returning to the ground. Sorry? Amirul ke?
Recombination.
Yeah, recombination, right? So it's the opposite of excitation. Excitation, if you go to higher state, right? Excitation. So if you reverse that, you're gonna get recombination. So due to this recombination, what do we get? Returning to the ground state, what do we get as a result, Amiro? As a result of recombination process? What do you get? What does it release?
Photon.
Yes, photons. Light emission, photons. Emission of visible light, photons. And as a result, you get to see the plasma. Okay. Tengok sini. You get to see the plasma. So it's in the radiative recombination process. Recombination. That's what we learn this in 306. Returning to ground state, right? So emitting photons. And you get to see the color from the visible light photons. So another process in sputtering is called RF sputtering. The first one that we discussed was DC, direct current. The second choice is RF, radio frequency. Radio frequency sputtering. If more than one electrodes are insulating, for example, if target is an insulator, if you have your sputter target as an insulator, apa contoh insulator target? Can you give example? You can write down, can unmute yourself. Apa contoh insulator sputter target? Anyone? Anything insulator? Let's go to Akilah. Akilah, apa contoh insulator sputter target? Akilah? What is an example of insulator sputter target? Sputter target yang insulator. Apa contoh? Example, anyone? Apa contoh insulator sputter target? Can write down. Kalau sputter silicon, is it insulator? Sputter silicon, is it an insulator? Anyone? Tungsten. Tungsten. Tungsten apa? W. Tungsten insulator kah? To check. Tungsten, is tungsten insulator? Lagi, other examples other than tungsten? Silicon nitride. Okay. Silicon dioxide insulator kah? Apa? Silicon dioxide. Silicon carbide. Insulator semua kan? Silicon semiconductor. Tungsten apa tungsten? Do you want to try search? Is it an insulator or not?
It's a metal, but it's a poor conductor of electricity. Poor.
Yeah, but it's a metal, right? Tapi dia tak high conductivity lah, right? So it's a metal. Tungsten is a metal. Silicon is a semiconductor. Tapi dia bukan insulator. Like insulator, for example, silicon nitride, oxide, carbide, many more. You ada oxide, tin oxide, no. Tin oxide is with good conductivity. TiO2 good conductivity, walaupun dia oxide. So there are other examples as well. So the point here is, if you use insulator as your target material, as your sputter target, you need to use RF sputtering. Okay? You need to use RF sputtering if your target materials are insulators. Why? Okay. If you use metals as your sputter target, you can use DC. Sebab dia conductive. Metals, we can use DC, RF, we normally use insulators. Tapi RF, you can still sputter metals. Okay? RF can do both, but DC can only do metals, right? So the sign frequency is 13.56 megahertz. So to be able to run RF sputtering system, you have pretty much the same thing on the inside, except vacuum sama, inlet sama, grounding sama, but the source is different. Okay, you use DC source for your DC sputtering, but for your RF you need to use RF source, RF power input, right? So to be able to use this RF power input, you need to use matching network. Okay, so you can add some adjustment in your matching network in order to deliver 13.56 megahertz, right? So insulators without RF, if you run insulators without RF, what's going to happen? So let's compare these two conditions. So if you have insulators as your target materials, as your spot target, but you don't use RF, so positive plus ions, AR plus ions strike negatively charged insulator or target. Okay, so let's see what happens. Your AR plus strike negatively charged insulator or target. So that will cause a decrease applied negative potential. Decrease applied negative potential until AR plus are not attracted to the cathode anymore. And then the voltage becomes less than that is required to sustain the glow discharge. Okay, as a result, so the voltage becomes less than what is required in order to continue the ionization process. Okay, kita tengok ionization for, right? Ionization is here. So voltage will become lesser and lesser and lesser, and eventually you cannot sustain the plasma, and the plasma just dies off, right? Plasma quenching. So if you use RF, on the other hand, for the insulators, electrons have high enough mobility to keep up with the changing field. Bila you run RF, you are running like that. Okay, you're running AC, yeah? The field's changing, right? Electrons have high enough energy to keep up with the changing field, but ions don't. More electrons than ions are collected. Each electrode, so the surface become negatively charged. So become negatively charged. Electrodes maintaining a self-biasing, so it will result in self-biasing steady state with respect to the voltage. And that will sustain the plasma. So process parameters in the sputtering. Okay, you have gas species. So if you compare DC and RF on the left and on the right hand side, so you can see the difference. You have pretty much the same thing in the chamber. The difference is in the VDC versus matching network. Okay, DC input and RF input, and this matching network is adjusted so that you can deliver 13.56 megahertz as your frequency of the system. Right, sputter deposition system. Kalau you dah biasa run sputter, maybe you can visualize this pretty much. Load lock is a place where we don't have load lock in our system in the lab. Okay, let me illustrate this to you. This is your chamber. Ini dalam chamber. Hari tu yang run sputtering siapa? Akilah dengan siapa? Izzati kah? Izzati dengan Akilah kan? Betul? Was it Izzati and Akilah? Right, okay, good. So, Izzati, did you see any load lock? Kalau bila you buka sample, you buka chamber tu, you buka chamber and you put your sample inside the chamber, right? Manually? Betul? Betul, Izzati? Kan? So, you masuk your sample inside the chamber manually, right? So, to be able to do that, you have to open the chamber. You kena buka pintu kan? So you have to vent the chamber so that the pressure inside the chamber is equal to atmospheric pressure. Then only you can open. Kalau dalam vacuum luar atmospheric, then obviously you cannot open because pressure difference. So when you open the door, the front door, to be able to bring in your samples. So the moment you buka je, the chamber will be exposed to the atmosphere. Okay, particles and everything, right? Particles and whatever whatever that we have in the lab, right? Particles and moisture and contamination, perhaps. Okay, the moment you open the chamber door. So as a result, your chamber will then be at atmospheric pressure, 760 torr. And you have all sort of contamination coming in, moisture, particles, blah, blah, blah. Okay, and you expose the chamber every single time you open to remove samples after you're done, or to put in samples when you want to start. So these conditions, these repeated conditions, will expose the chamber to the atmosphere, and that will increase the likelihood of contamination. On the other hand, if you have a system that has a load lock ni dia macam satu step ataupun satu mechanism where you put your sample here, you put your sample dekat satu arm, if you like, arm, but this chamber and the arm is isolated by a valve. Maknanya, bila you ada load lock, your chamber can remain at 10-5 base pressure. Your chamber can remain at 10-5, no contamination, no frequent exposure to the environment, contamination, particles, moisture, whatnot. So it remains at 10-5 after the sputtering process, because your samples can be removed or put in by using a load lock. Okay, maksudnya bila you run your sample dalam ni, you run a sputtering done, for example, you're done. What you have to do is you have to open this gate valve. Ni gate valve, macam pintu lah, to isolate your chamber and your load lock. Okay, yang kiri ni load lock. Right, so you make sure that your load lock is at the same pressure with the chamber pressure, 10-5, and then you have a robot arm to transfer your sample into the load lock after you're done. Then the moment you transfer your samples into the load lock, the gate valve is closed. Maknanya chamber dengan load lock is isolated. So what happens here doesn't affect what happens here. So you can then maintain the chamber at 10-5 and it's isolated already. So then you can vent. Vent means you can increase the pressure in the load lock to atmospheric pressure. Okay, load lock ni, you vent means you increase the pressure to 1 atm or 760 torr. 760 torr. And that will reduce contamination to the main chamber, because load lock is not the main processing chamber. It's just a mechanism to transport your wafers and your other samples. Okay, so you vent the chamber to 760 torr or 1 atm, then you boleh ambil sampel keluar, while the chamber is still at 10-5, because there is a gate valve isolating chamber and load lock. Okay, so in that case, you maintain the purity of the chamber, the cleanliness of the chamber. So bila you nak masukkan sampel baru, you just masukkan sampel dalam load lock, then you purge the load lock. Purge the load lock means you vacuum the load lock down to 10-5. The moment the load lock pressure is equal to the chamber pressure, you open the gate valve, transport the sample into the chamber, close the gate valve, and then you can leave this one for a while, the load lock for a while, then you run your process. Habis je, you masuk balik hantar dalam load lock, then you vent the load lock, remove sample, masuk balik. So you are only venting and purging the load lock instead of the base, the chamber, right? So that will protect the cleanliness of the chamber. So minimize the amount of air and other contaminants that will be introduced in the chamber. So this is the best way to run a vacuum system. Okay, tapi dekat kita punya lab tak ada load lock, right? So you have to open the chamber, masuk sampel, keluar sampel, tutup chamber. So every time you do that, you are actually exposing the chamber to outside particles, cleanliness, contamination, moisture, and whatnot, right? So the best way is to have load locks. Then vacuum pump, that will bring the pressure down to 10- whatever, according to what you need. A sputtering chamber, depending on what you have. Ada yang industrial scale, ada yang lab scale, ada yang panjang in multiple configuration, right? Multiple chamber to hold different targets. So if you're talking about different target material, then you may need to use different chambers. For example, macam saya cerita tentang Fuji Electric tu, 20 different chambers. Then habis one, then the gate valve will open, transporting to the next chamber. Done. So multi-layer punya deposition. So without breaking vacuum. Without breaking vacuum, maksudnya your respective chamber can be at the targeted vacuum level, say 10 minus 5 minus 6 store. So bila you transfer from chamber 1 to chamber 2, you don't have to change the vacuum level. You can just transport at the same vacuum level, right? So that will keep the purity of the process and throughput as well. So target mounted to the cathode to keep in contact with water-cooled backing plate, right? You need backing plate. Wafer heater, if there is any heater to the wafer, you can also heat the wafer while doing the sputtering process. So in this case, you if you need to run your sputtering, say at 200 degrees C, 300, 500, 550, and whatever, so you can just change the pressure, no, the temperature of the wafer plate, right, in order to vary the substrate temperature. And then the power supply can be DC, can be RF, depending on DC or RF sputtering. So again, this is pretty much the same thing like the plasma formations now. We use DC or RF in parallel plate arrangement, and then cathode, put the target on the cathode, and then the substrate on the anode, and then AR gas, ionization process, and then spotted target atom to travel to the substrate. This is where the mean free path comes in, right? So your distance has to be less than MFH, or MFP, sorry, MFP has to be bigger than H, or the physical distance between your target and your substrate, right? Spotted atom arrive at substrate and implant bounds, blah, blah, blah. So depending on the energies of the process. Right, this is another illustration of the process. So again, plasma, then you are sputtering AL target in this case. So that means you punya target material is AL, and you want to coat AL on silicon, for example. Silicon, and then you not coat aluminium, say 100 nanometer. So we need to use AL target, and then so that's pretty much what's going on in order to do the process. So spotted atoms angle of arrival. Remember last time when I talked about unidirectionality of the process? Still remember? When you talk about unidirectionality, which process is the most unidirectional? Proses mana yang paling unidirectional daripada apa yang kita dah belajar? Which one is highly unidirectional? Anyone? Haziq, which one is highly unidirectional? Hmm? Okay. Don't look at this AB yet. Proses mana dalam thin film deposition yang paling unidirectional?
And isotropic.
Proses mana yang paling unidirectional?
And
Daripada thin film deposition processes. Yang mana yang paling unidirectional, yang mana yang paling omnidirectional? Remember last time we discussed unidirectional and omnidirectional. Proses mana yang paling line of sight or unidirectional daripada semua thin film deposition process? Uni satu arah, omni banyak arah. Proses mana yang paling unidirectional? Anyone? Mimi? Proses mana yang paling unidirectional? Daripada apa yang kita dah belajar dan belajar sikit-sikit sebelum ni. Anyone? Go. Apa maksud unidirectional? Sakit dah telinga pakai ni. Anyone? Unidirectional yang mana? Macam mana unidirectional?
Anisotropic.
Anisotropic is not a process, right? Ni proses name, nama proses. Anisotropic betul lah memang ada unidirectional. Tapi what is the most unidirectional punya proses? Proses apa yang paling unidirectional? Nama proses. Dalam thin film deposition. Alia? Proses mana yang paling unidirectional? Menurut E. Evaporation, right? Evaporation, paling unidirectional. That's it. Thermal evaporation, electron beam evaporation, line of sight, it goes straight up. Kalau dia ada cone pun dia buka pun just very little. It's highly directional. That means if you have features on the wafers, if you mount at some angle, perhaps if it's not well rotated, then you will suffer from shading effect on the side of the structures, right? Okay, on the other hand, proses mana yang paling omnidirectional? Yang paling unidirectional, evaporation. Yang paling omni apa? Tak belajar lagi ni, tapi saya sebut sikit hari tu. Proses apa yang paling boleh cover banyak arah? Multiple angles, deposition. Menurut C, CVD, right. CVD, paling omnidirectional. Paling unidirectional, evaporation. Paling oblique angle. Oblique tu multiple angle lah, high angle. Paling boleh pergi banyak arah ialah CVD. Proses apa yang tengah-tengah? Can be uni, can be omni to some extent. Sputtering, okay? Sputtering ni tengah-tengah, right? Maybe sputtering tengah-tengah. It's uni to some extent, but it's omni to some extent. Yang paling omni ialah CVD, yang paling uni ialah evaporation. Sputtering you have both depending on the situation. So kalau you want to be unidirectional and yet you want to have some omnidirectionality, then you have to use sputtering. If you want to go for completely omnidirectional, then you have to go for CVD. If you don't care, you don't have issues, you don't have any concern with unidirectionality, you can just go for electron beam evaporation. Okay. If you compare these three processes, these three main processes, divide DCRF, thermal, E-beam. Okay, kalau you just compare these three processes, evaporation, sputtering, CVD, paling omnidirectional adalah CVD, paling uni adalah evaporation, sputtering is in the middle. If you compare in terms of deposition rate, yang mana yang paling tinggi that rate? Maknanya in a very short time you can get high nanometer per minute, high micron per minute. That will be evaporation. Evaporation has the highest that rate. Sputtering has the middle one. CVD has the lowest one. Okay. Okay, that rate, deposition rate. So that means if you want to run within the same unit time, comparing the three processes, you akan dapat paling thick sample guna evaporation, medium sputtering, paling thin CVD. Tapi if you talk about uniformity of deposition, paling uniform ialah CVD, second uniform ialah sputtering, paling susah nak dapat uniformity ialah evaporation, right? Depends on sample condition juga lah. That's just a general process punya capability if you like. But if you have a sample with the right geometry, the right feature, rotation, blah, 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 you can also ensure good uniformity by evaporation process, right? So if you compare sputtered atoms, angle of arrival, this is just talking about sputtering. Don't worry about evaporation, don't worry about CVD. So if you talk about sputtering, let's talk about the angle of arrival of atom. So if you have just 1 point sputtering and this is your wafer, okay, if you have a point like or target like, so to be able to cover the whole wafer, your sputtering has to be like that, quite omnidirectional, isn't it? Kalau di unidirectional je, dia akan tak akan dapat cover the whole samples, or perhaps if you have some of the wafer here, uniformly, that cannot be done. Okay. So it can be wide depending on the geometry, narrow angle of arrival depending, anisotropic deposition to some extent. Okay, that means the way you mount your wafers cannot be too wide because sputtering punya omnidirectionality or unidirectionality is always in the middle. Okay, so that means you have to sputter and see what you get. So if you have a large target, for example, the sputtering can happen from multiple points. Okay, so that can ensure wider angle of arrival. So, but you can sputter from multiple points compared to just a small sputter target. So that can ensure a more isotropic deposition. Ataupun dia lebih uniform across wafers, across center to edge. Sebab bila you sputter nanti, when you run sputtering or evaporation or CVD, it comes with characterization, right? Remember, processing followed by characterization. So if you talk about characterization for this particular process, then kalau you sputter satu silicon wafer, for example, then you want to know what is the thickness in the center, what is the thickness on the edge. So maybe you have a couple of points during your characterization. So you might want to know all these points when your thickness uniformity, right? So not only that, you might need to know as well, if you have multiple wafers in the batch, in the same batch, how about the center for wafer 1 in comparison to center for wafer 2? Or how about edge for wafer 1 in comparison to edge for wafer 2 or wafer 3? Okay, so it can be across one wafer, it can be across 2 different wafers, it can be across 25 wafers. So it can also be across batch to batch. So that's how characterization comes in, right? So we've covered this one last time on the step coverage. So if you talk about the sputtering step coverage, if you have features existing on your wafers, for example, then you will see the spectrum. Sputtering will be in the middle, evap will be on the worst side on the left, CVD will be on the best. Okay, so if you talk about step coverage with features, comparing 3 different processes, then sputtering will give you a better step coverage than evaporation. Maknanya dia better than evaporation, but it's worse than CVD, right? So that's why I told you, when you talk about uniformity, step coverage, the best is always CVD because of its omnidirectionality, right? The worst will always be evaporation due to its high directionality ataupun unidirectionality, right? So kalau ada feature, then certain places will not be covered, right? Certain places will not be covered if you have a shading effect. So for example, if you talk about if you have, say, two different conditions, you have you want to coat your glass, you have a glass substrate. Okay, glass substrate kosong, you nak sputter atau you nak deposit silicon, say 1 micron thickness, and your glass is perhaps 3 mm thickness. Okay, not to scale, tak ikut scale betul lah, 1 micron. So it may be okay, it may be easy to do that on planar glass, but if you talk about the other glass, textured glass, yang rough surface, if you have the very same glass, but then the surface is roughened ataupun textured in this case, okay, and you want to deposit the very same thickness of silicon, 1 micron. So in this condition, in the second case, you will have difficulties to coat at high angles here, at high angles. Mungkin you akan dapat like that, so it will not be. So if you coat a very thick layer, then you'll probably not see any issues on the step coverage. But if you coat a very thin layer, kalau you punya layer very thin, any glass. If you lay it very thin, then there may be areas that are not covered. Okay, so due to this stat coverage issue, okay, ini pun sama. So lack of directionality makes filling of high aspect ratio VR difficult. Okay, so we learned that if you want to, in certain conditions, you want to have high directionality. High directionality. The point high directionality means unidirectional. In some other cases, you need to have a more omnidirectional type of deposition. Okay. Ini sama process parameter. Okay, sputtering process parameters. How many more pages do I have? Okay, let's just finish a few more slides. Okay, you can actually vary many process parameters during the sputtering. So semuanya you boleh vary ya, bias, voltage, substrate temperature, the pressure, gas, right? So if you vary those, so you can create many different sputtering conditions. Okay, so for example, if you increase AR pressure, your sputtering of the target will increase, sputtering of the film will also increase. For example, you can increase the bias, you can use negative bias to accelerate ions to the target, for example. Okay, so you can do many things. You can increase AR pressure to increase collisions. Sebab lagi banyak AR atom in the atmosphere, then you will have more collisions between each other. So that means shorter mean free path, and that means a more isotropic arrival of the atoms. Okay, so heating can also be used using substrate temperature, for example. You will apply heating to the substrate in order to improve planarization in some cases, right? So maksudnya when you say glass, when you have atoms deposited, contoh, saya look at assessing. When you have aluminium deposited on glass, if you supply, no, so let's say this is silicon. If you attach this to some kind of heater, then the arriving atoms can have some mobility. Okay, dia boleh masih bergerak. Dia boleh masih boleh bergerak upon arrival because the substrate is heated. Okay. On the other hand, if you don't apply any heat, then they just arrive and that's it. They just landed there and not moving. Yeah, I think I'll just stop here. So those are called basic sputtering process. Okay. Next, tomorrow we're going to learn still sputtering, but we call that as reactive sputtering. Reactive sputtering means whatever you have in the sputtering process, you have reaction, additional reaction with the gas. Maksudnya, for example, you can, if you want to deposit silicon nitride, you have two options. Option number one, you can sputter from silicon nitride target. If your target is silicon nitride and then you run sputtering, then you're going to have silicon nitride deposited on your silicon or glass or whatever, right? So that is option number one, the typical sputtering process. Option number two is called reactive sputtering, where you can use silicon as your target. So use silicon target, but then you inject nitrogen gas into the chamber and then induce reaction between silicon and nitrogen at certain flow rate. Then they will have reactions producing silicon nitride as a result of reactive sputtering between silicon target and nitrogen gas. So that can still produce silicon nitride, and you can in fact vary the stoichiometry of the process. Stoichiometry here means the silicon X, nitrogen Y. Okay, stoichiometry. You can vary the stoichiometry, and then as a result, you can actually vary the refractive index, extinction coefficient, and some other perhaps roughness and thickness and that rate and so on and so forth. Okay, and that is called reactive sputtering, and we'll discuss over that topic tomorrow. Okay. Okay, any questions so far? Is it okay so far, sputtering? Nope. Okay, tak ada soalan. Then I'll see you tomorrow 11 then. Right? Bye bye. Take care. Assalamualaikum.